Okay, so welcome to this what to call first session of the last day, right? So you already had so many lectures and lab sessions. Yeah, so maybe we begin with this one. So it's like non-contact sensing using piezoelectric and structural materials. So primarily, like this topic, non-contact sensing has been, I mean, considered. So first, we could talk about, say, what could be the possible motivation to have this, right? So, some of you I see might have been involved with some kind of sensing actuation applications, maybe others may not be. But in general, like if you try to make use of a sensor, then what we do is we try to place a sensor on the particular structure from where you want to have some kind of information. Okay. So of course, we have the wired connection associated, right? And then say one simple example what I can give is like fault diagnosis. If you consider, suppose you have a large panel and then say any small micro crack develops and then you want to have it using piezoelectric material, whether it has occurred, then what we need to do, we need to place the piezo patches at different locations, probable locations where the faults may occur, and then we need to take signal from each particular area. So all in all, like depending on the complexity of the structure, one thing, and depending on the size, we might end up say having number of such sensors to be placed. Okay, so then if as the number of sensor patches increases, then of course we'll have as many wired connections also increasing. So this way we may end up having quite a web of the wires, right? So one motivation is that if we can have this sensing part at least in non-contact mode, then we may get rid of these all web of wires. So that is one motivation. And then of course other possibilities or say other motivation is like when we have to fix any additional thing on any structure, then the properties of the structure will get modified. Like if some of you might be doing vibration stuff, right? So if you put a proof mass, you get different natural frequency range, isn't it? So likewise, if you place a patch or sensor of any other kind, then that will again modify some properties of the structure. So if we don't want to say affect the properties of the structure, then we may try to have a structure which by itself can give some kind of signals, and through them we can try to have some information about the structure. So oftentimes, of course, the primary objective is to get a fault diagnosis or say health monitoring. So are there any kind of say micro cracks or some kind of other damages occurring within the structure? So that kind of information we can try to extract them. Yeah, so with that motivation here, of course, some basic studies I would call which we did. So I'll just try to brief those. Okay. Yeah, so to begin with, this is the usual procedure to first of all make a piezoelectric material. So what we have been using generally are the in the pellet form. So you actually, depending on which piezoelectric material you want to make, you have to have these precursors, right? So the precursor powders in the stoichiometric ratio you have to first of all mix, then you put it for the calcination, high temperature, so then the desired material powder will be made. And then generally we desire it in a pellet form. So this powder then is to be first of all pressed in a hydrostatic press usually is used for this purpose. So with that actually it gets bound in this fashion, and then you have to again center it so that it attains enough strength. Okay, so finally you may have a pellet like this. Okay, So this is the usual method. I mean, there are other methods also, but this is what generally is followed in the lab. So just I thought a brief could be included before we proceed further. And next, this in an effort to obtain some non-contact signals for the sensing purpose, the initial experiments what we conducted, so those were by providing some electrical input, right? So generally I think piezo patches, everyone, wherever you see the application, and some kind of force is applied, right? Either it is pressed or whatever, and then you get some output voltage and current output. Okay, so rather than that, we initial for the initial experiments, we had actually given the electrical signals as the input. So this is just a schematic. Is this cursor visible nicely? Hmm? So yeah, so this is supposed to be, this cylindrical one is supposed to be the sample of a piezoelectric material. For this case it is BNT-BT, but yeah, I mean, any piezoelectric material if you use, then we are likely to have the signal, so that's not a problem. So then it's placed on this insulating base, and then this copper loop we placed. This is simple copper sheet, it's wound around it. It's not connected to this, it's away from this, right? And then this is connected to the oscilloscope. You have seen these similar ones during your lab, right? So this is for receiving the output, and then for the input at the two ends we made electrodes, right? And connected the wires, and then this is the power source, and using the power source we gave the alternating current input. So for those who are a bit familiar, if you want to have, say, some output from a piezoelectric material, right, then the input has to keep varying. Like I mean, here it is electrical input, but let me give the example of force input only. Suppose you apply force, you keep it at that, then your signal or voltage, whatever you are getting, will actually get lost after some time. And that is so because in whatever state the material is stable, all the atoms, unit cells, they tend to actually rearrange themselves, and finally again attain a equilibrium. Okay, so anyhow a change is actually desirable to have continuous output. Here of course it's oscillating, I mean, the amplitude is continuously changing, right, for alternating current. So your variation is also occurring with time continuously, and then we can have signals. So moving on to the next slide. Yeah, so here we have this XRD pattern, and so the left one, this one is the usual XRD pattern what is obtained, and this is the expanded form. So this particular material which has been chosen, it has got two components as you could see here. So one particular component, so you see this actually is varying from 4 BT, 5 BT, 6 BT, 7 BT, 8 BT, like that. This fraction of BT is varying, right? So this middle one, if you consider the 6 BT, this actually gives a specific thing, that is two phases coexist for this. So because of this existence of two phases, here the names also are there. So like for this this one and this one, that is the first two, right? This one and this one, right? Here you have this and this. So these are rhombohedral, and the last two, 7 and 8, these are tetragonal. Okay, so tetragonal of course is like when your cube becomes more like a rectangular parallelepiped. Okay, so that is one side will be stretched, and for rhombohedral like a rhombus. As you convert square to rhombus, its 3D version will become that a cube becomes a rhombohedron. Okay, so that kind of structure it is. Yeah, so the point is like for this particular one, we have both the four phases. Like here you have tetragonal phase for the higher fraction of this, and here you have for lower fraction rhomboidal. But for this particular, both coexist. So because of that, this peak splitting actually confirms that this is happening. Okay. Yeah, so choosing this one composition is for the reason that because of the coexistence of these two phases, this tends to give better properties as compared to the other two combinations. Okay, so yeah, so that way it is a popular material. So yeah, so this was about this existence of two phases, and then we can have a look at the results. So this is the output, what is depicted in this diagram, and then again you have this fraction varying, and accordingly what kind of different graphs have been obtained, that is shown. Now interestingly, like I mentioned that for this two-phase system we are supposed to have good properties, right, or better properties as compared to the other two options. Okay, but rather than that, here just the opposite has been observed. This thicker one is actually representing the MR voltage what is obtained for the 6BT, which ideally is supposed to give better results, but here it just the opposite. Amplitude for other cases is high, for this is lower. And for the comparison, this bar chart can also be seen. So the 6BT is representing the voltage at this location. Okay, so this is kind of giving the minimum value. So then hereafter, like if I go to the next slide, yeah. So here you see we then here we have the plot in this as of the voltage, EMR voltage, or the non-contact signal voltage versus this electric field or applied electric field, I could say. Okay, so as the applied electric field strength is increasing, increasing pattern here can be observed, right? And again here this lower graph, this is meant for this BNT 6BT, again the same composition what I was mentioning. Okay, so here now if we just compare this last one with the remaining four, so what you see is that here these are more or less giving a continuously increasing trend as this applied electric field is increasing, right? But for this one it's not like that. So we got a data scatter of this kind, and we could fit one line here and one line here, essentially just to identify that what kind of slope the curves is data points are having. So now if you consider, then both the lines actually have distinctly different slopes, right? So this one has a less slope, but this one has a steep higher slope, right? So here what we can consider, say this point precisely is the transition point. So as you increase the field from here up to here, then the increase in the output, or the output for our case is the voltage. So voltage has got a linear increase, but it is at a slower pace. But beyond this, if you start further increasing the voltage, then steep curve is often. Now actually our what do you call this input voltage machine limitation is there, so we could not actually test beyond this, right? But this trend at least gave us a reason for the lower performance of this material. So here what we can consider, actually this two-phase system, like we had seen that there are two different kind of uh, structures what are observed, and both are existing there. So primary reason which is associated for the better performance is it's having large number of polarization directions. If you have bulk material, you will have different grains. All different grains will have a particular lattice structure. So if it is rhombohedral, then different orientations are possible, and same way for the tetragonal. Now, with each of these, there will be certain specific polarization directions. Like when you apply external electric field and the material gets polarized, so that will be under along certain specific direction within the unit cell, but not in the all the directions. So each one of these has got certain preferred polarization directions. Okay, so what happens is when we have this dual phase system, then you actually get benefit from the polarization directions of both the systems, and thereby it actually gets higher strength finally, or a higher polarization, I would say. Okay, so here, like this particular trend then tells us that this benefit of the larger number of polarization directions can only be harnessed when we are going for higher voltages, that is when the applied field is of higher strength. But at lower level, there is more resistance offered by the phase boundaries. Phase boundaries always offer resistance, like I don't know, at least for grains you must have uh, considered this, right? Particularly like suppose if mechanical point of view, I say strength is higher when you have smaller grains, right? That happens. I guess anybody from mechanical will be familiar with it, right? That is so because grain boundaries offer resistance. So similarly here, like phase boundaries will offer resistance when we try to polarize. So that resistance here is dominating at the lower voltages. But as we go for lower electric field, sorry, when we go for higher strength of the field, then we get benefit of large number of polarization directions, and that becomes dominant, and thereby better performance is achieved. So considering this variation, we can see that if we could go for the higher ones, we'll have this will surpass all this, and finally the usual thing what is observed will be observed for this case also. And additionally, we have this EMR voltage versus polarization. So here also a good correlation we could obtain. So the what we see is if the extent of polarization achieved is kind of proportional to the voltage what is obtained. Sorry. So this very nice say what do you call correlation, I mean, allows us a different measuring technique also. Like if you want to know the extent of polarization, you can actually measure this non-contact signal, and then you could give a information to what extent the polarization has been achieved in the material. So this is for the electrical inputs, and then next we moved on to the deformation induced signals for this from these piezoelectric materials. So yeah, of course, so deformation remains the main motivation, that when a structure is loaded, and then due to loading, whether are we ending up having some excessive loading, can we have that kind of information by not putting a sensor in direct contact, rather being away from it. Okay, so with that intent, these further experiments were then carried out. So these again the very initial trial experiments, I would say. So again here this bit is schematic. So on a fixed support, again it is to be insulated one, and on that PZT cylinder of this kind is placed, and then a copper sheet is wound around it, and then impact load is applied using a hammer. So then with this we of course could obtain the signal. So that's what is depicted here and here. So this is the signal which was obtained using a metal hammer, and this is with a plywood hammer. So here we got a bit more fluctuations, but yeah, of course it stabilizes after some time. So this, I mean, yeah, this was a beginning experiment, or where we could just first of all check whether any signals are received at all or not when we try to deform it. So after this, then a bit more say systematic study, I could say. So then this is the schematic again of the setup to carry out the loading. So here loading again, like with the hammer we applied impact. Here also impact will be applied, that is the consideration. So this one is actually simply a rod which has got certain holes at successive intervals, 3 centimeters precisely. So then this is an annular weight which can slide over it freely. So the idea is if you could keep it at different heights and then drop it, so certain say measurable kind of impact will be applied. Depending on height, we can consider how much potential energy it will be imparted to the, I mean, the sample. And then we place these bakelite plates here. So bakelite plates, I mean, so that we have insulation, because again, like you might know, when you have a material like this, which is ferroelectric or piezoelectric, and then say you apply some load, then some charge will actually get accumulated on the primary surfaces, top and bottom one, we can say. And now suppose if you have a conducting material attached to it, then the charge will actually get immediately transferred. So if that happens, then we may not get any signals. So for that purpose, it has to be insulated at the top and bottom. So bakelite plate also provides support, but it also insulates. So both the things then we could have with this. So that is the benefit. And then again, this thing remains same, that copper sheet is wound around it, not touching it. So with this then, as from the different heights, the weight is dropped onto this, so we get different signals. So here this is showing the variation of the voltage obtained as this height of impact is changed from, like, it's from 6 centimeter up to 24 centimeter. Okay, again more or less a linear variation. And then just for the sake of comparison, two grades, one soft PZT, one hard PZT, these are compared. So yeah, for the hard PZT actually you require a bit higher load to actuate it, so that's why this is giving comparatively less amplitude, and this is giving the higher one. But yeah, both are more or less varying linearly as the height of impact is increased. So some correlation with the applied load and the obtained signal we have here. And yeah, this is with a bit different setup was to be made particularly for some other reason, but yeah, all the same, this is a different setup here. This complete thing is made of steel, so that's why this green one again is representing the insulation, because it was made of steel, so we had to place a separate insulation here. So now when this platform is say released from height, then again it can apply sufficiently high impact, and the material can then give any signals based on the same. So we tried to have this height, and this was a bit what do you call, adjustable. So this is to be adjusted according to the height, so that when this platform hits this, it's horizontal, and therefore the load is applied uniformly on the entire surface. So that was ensured. And with this also, like as this inclination of the platform is varied, linearly increasing signals are obtained. Yeah, so fine. Then beyond that, then we moved on to effect of poling. So polarization, I guess some of you already might be knowing. So as such, I mean, naturally many piezoelectric materials occur which are by default piezoelectric. Okay, but there are a large number of materials which are actually under this category ferroelectric materials, and if you polarize them, then they will be acting as very good piezoelectric materials, right? So most of the popular materials, including this PZT, I think many of you might be working also. I don't know. Some of you are working already, PhDs? Yes, right. So PZT also is a ferroelectric material which actually, when polarized, actually gives very high performance. So that's why it's very much popular also. So we actually considered some unpolarized samples, and then with again available polling field, we don't have pretty high polarization setup. So to whatever extent it is possible, we polarize them and then again try to obtain these results. So increasing pattern, with that also we could obtain. Here this is the D3 constant measurement. Again, if this is, I mean, the abscissa is giving the polling field, that how much electric field was applied to polarize it. And then as this is increased, then T33 constant is increasing, and similarly the a higher EMR voltage signal also could be applied in increasing fashion. Yeah, next is this effect of different environmental conditions, like I mean, suppose the material continues to perform the same when higher temperature applications are considered, or low temperature conditions are considered. So this one is for higher temperature. So this setup completely, a complete setup was placed inside the environmental chamber, and then you have to have of course all the heat insulation so as to safeguard all your instrumentation wires, etc. So this complete setup was kept inside, and then you heat it up, you let it stabilize for some time, and then this platform is dropped so that you observe the signal. So that is how the experiments were conducted. So this shows the variation. These are just sample plots of the signals what are obtained, and here you have the EMR voltage versus temperature. Yeah, so temperature is in Kelvin here. So the first value could be considered for the room temperature. Yeah, so as you can see, it is relatively less, of course, because in Himachal room temperature is less. But if you are somewhere else, then maybe might have begun somewhere away from this, close to 300 maybe. Yeah, so anyhow, so this is again, as the temperature is increasing, so we have a decreasing EMR voltage. That's what is observed here. Let's see. Yeah, so here just to explain the reason. So again, like these materials, ferroelectric materials, they always can give their properties up to certain temperature, right? So I guess again that also those who are working know it already, right? Yeah, so name is also here, right? So Curie temperature you are aware of, I hope. Huh? How many? Everyone? Those who are using piezo patches. Huh? Amit? Curie temperature you are aware? No. No. Okay, yeah, so yeah, generally we keep using things on room temperature, so we don't need to bother those who are in the application areas. But yeah, so actually these materials have this piezoelectric property only at up to certain temperature. Beyond that, it is lost. So the reason is like this, of course, is schematic. So arrows are just representing that material is polarized in this direction. Okay. So if it is polarized in this direction, then suppose if it is heated and the temperature increases, then all its molecules will have higher energy, so they will have more vibrations, right? So as a result, what will happen? This this polarized state that we enforce in a way, we apply high electric field, we polarize the material. So due to that then stays there, because there is a resistance for coming back to the original position. But when they get heat input, so their this thermal energy causes higher vibrations. So then again randomness increases. So rather than being aligned in one direction, they actually get randomly aligned. So as the temperature increases, this randomness continues to increase, and finally this Curie temperature is the location where it becomes more or less completely random. So then, since this polarization is lost, this piezoelectric effect is completely lost at this temperature. So that is the reason that as we keep increasing the temperature, this higher randomness causes a weaker signal at higher temperatures. Okay. Yeah. Next, we also considered experimenting with the low temperatures. Okay. So yeah, this is again the setup which I had explained for the first time. So for this case again, this was kept inside the environmental chamber, and then now we reduce the temperature for this set of experiments. Here we actually have used liquid nitrogen for cooling it. So, and of course with liquid nitrogen you have a limit, so we could only cool up to minus 70 degrees centigrade. So below that we could not cool it down. Okay, so these results are up to that extent. And yeah, so this is again the XRD pattern for the material, PZT material of course, and then you have this variation of EMR voltage with the temperature. Yeah, so we see at low temperature lower signal and higher temperature higher signal. So actually experiment in a way was opposite. This is the room temperature, and then beyond that we continue to decrease it. So here like for the increasing temperature also decreasing trend was observed, and here for decreasing temperature also we observe a decreasing trend. Okay. And yeah, and additionally we tried to calculate the energy release rate associated with the signals. So like this is the usual voltage versus time plot. So if you want to have say an assessment of the energy associated with the signal, so what for a transient signal I would say, not a continuous one. For continuous signals you go for assessing the power rather than energy associated. So here if you have the square of the signal, so then this V square with respect to T, this actually is a quantity proportional to the energy of the signal. So area under the curve if we consider and then divide it with the total time for which the signal is stayed, so that gives us the energy release rate. Okay, a quantity proportional to energy release rate I would say. Okay, so this also was calculated. So for that this square form we had to generate. And yes, so this decreasing pattern we had, so a discussion about that we can have in the next slides. Yeah. So in order to have a possible explanation, we had also conducted some this mechanical test. So we tried to obtain the Young's modulus. So for that we use the strain gauges on the samples, and then we applied a static loading, and then uh, with the strain measurement and using the two values we finally got this Young's modulus. So this again gives the variation of Young's modulus. So here we are close to the room temperature value, and then as the temperature is increased, the Young's modulus is giving a increasing trend. So that's what is observed, right? And this graph is giving you the both of these together. So we can say as the temperature is reduced, Young's modulus is increasing and the EMR voltage is reducing. So what do you call, now here I mean this simply can then be associated with the deformation, right? So if Young's modulus is high, that essentially will mean that the sample will have a higher stiffness. So as we keep decreasing this temperature, the sample tends to attain higher stiffness. So the same load will then produce less deformation for a higher stiffness material, right, as compared to the lower stiffness material, right? So thereby, since the deformation is less, we get a weaker signal. So this is kind of linked with this. And yeah, then additionally we had tried to plot this energy. So for that we plotted this AMR energy release rate with HF by KT. The thing is like this product of Boltzmann constant and the temperature. This actually is a quantity which is proportional to the thermal energy. So just we use this ratio, this HF you can identify as the energy of photon or the energy of the signal emitted, and this ratio and this energy release rate. So we got a good relationship with this. Then moving on to electromagnetic radiation from cement based material. So like I mentioned, so one motive of course is to first of all be able to have non-contact signal. So we started with piezoelectric materials, which by default they have been much used for the sensing application, and then we achieved non-contact sensing using them. And next is this effort to say have some kind of signals from the cement based material. So particularly the intent is to finally get some signal from the structure. So if structure and cement is the most commonly used structural material, so if we can get something from it, then we can expect that okay, from the structures also we can get some kind of information. So that is the motivation. So yeah, to begin with, maybe I can have a little water. Yes, so you have this smaller samples. First of all, we had made this image is showing some samples where, so in image it seems they look much bigger, but this is the size, right? They are very small samples. So 22 mm diameter and 22 mm height. This is the usual size what they have. And yeah, this cement and water ratio 3:1. So gradual mixing, and of course you might have seen the process of making such a thing all the time. So gradually after mixing cement with water, that is placed in the mold for 24 hours, and thereafter these were soaked in water. Okay, so ideal is to cure it at least for 28 days, right? But of course for the experiments we did in the some intermediate values also. So like 3 days, 7 days and 28 days like that are generally given in codes. So we followed that, and we also increased one more value in between so as to have some better variation. So yeah, so these samples and the same setup, maybe I'll skip this, and here are the signals. So now I mean for the pure hydrated cement paste also we could get some signals. So again this graph, if you compare with the previous one for the PZT, it's more or less same, right? A linearly increasing graph. But of course we have to also see this. So here this is in millivolts, and for the PZT it was in volts. Okay, and there also I guess we had gone up to 120 or something, but since this is in millivolts, so you can just compare. The order here is less by 10 to the power 3, so you have to divide whatever we achieve with PZT by 10 to the power 3, then we are somewhere for the actual values from this cement. But all the same, it's I mean a happy finding, because cement is the most common structural material, and at least some signal we are directly obtaining from the cement. Okay. Yeah, and then like I mentioned, so generally this 3, 7, and 28 days of curing are the like days mentioned when you actually can observe the strength of the uh, cement based hydrated material, so that I mean you have a better understanding whether the process is occurring properly and so on. And 14 we had added as an additional so as to have a proper variation for the study. And these all linearly varying graphs are again EMR voltage versus the height of impact. So for 3 days we actually got pretty high values, as you can see here. I mean, for a 6 centimeter height of the wet drop, you have about more than 500 millivolt signal, right? But then after 7 days of curing, this suddenly drops. So these three lines are 7, 14, and 28. So it continues to decrease beyond 7 also. The decreasing trend is there for the voltage, but here it is very sudden from 3 to 7 days. Okay. So largely, of course, like some of you might already know, you are from civil also, right? More people from civil, you are there. Okay. So you probably might know already that cement actually tends to continue with hydration forever, ideally like that it is mentioned. But at least until 28 days, of course, we consider the values. So all in all, what happens is the reaction is slow. I mean, the point is the reaction is slow. So it takes time. So initially, this part, if we consider, here hydration is to a very less extent. It does not attain the strength. Everyone might have seen, no, when a structure with cement is built, then you keep curing it for a pretty long time. No? At least for 14 days, they are kept as such, and thereafter you proceed further, because it takes time to attain the strength, any cement based structure. So that is because this reaction actually takes longer time for this. So effectively, as that continues to occur, it gains strength. That is one thing. And also this water, we keep soaking it with water, so it continues to absorb that, and that water becomes part of the reaction. And then this CSH gel, it is called, usually it has got all the hydroxide, oh sorry, all the oxides, calcium oxide, and then silicon oxide, and then water also is an oxide, of course. So together this gel formation takes place, and that actually is the uh, that is how it gets solidified or becomes a solid strong material. Yeah, so yes, so this yeah, this point I missed. So like at the stage of 3 days, actually you have ample amount of free water also available within the material. Thereafter, it becomes part of the this hydrated product. So just to confirm that, here we actually have done some experiment with removing the moisture content also. So these two graphs, maybe you can see, these are for the EMR voltage. So this is for like when the sample has been cured for 28 days and then taken out, let it dry in air just like that, and then test it. And this one is when you keep it in oven at a mild temperature, only 100 degrees centigrade. Okay, so that actually causes any possible water evaporation. So thereafter also this much voltage we could get. I mean, this is getting reduced, but all the same it continues to be there. That means even if the structure could be dried because of heat, it will continue to give some signal at least. So that was the intent. And the opposite also is done over here. You see, dried sample, again if water is added, then the signal actually tends to increase. But of course, it attains a saturated value. Beyond this, no other further increase. Even if you add water, it won't be able to further absorb, or further increase in signal won't take place. And yeah, there is this good correlation with the voltage, and the inverse of the strength we had plotted. Plotting inverse was just for the purpose of seeing whether the graphs are having similarity, nothing else. So you can say as the strength increases in the opposite uh, fashion, the EMR signal reduces. Like that we could consider from this. Okay. So it's a, I mean, good correlation with the increasing strength. In the same kind of proportion, you have a decreasing signal. Same kind of what do you call variation, you can say. And then these are just bit different trials uh, by changing the fly ash content. Okay, so this is the variation in compressive strength, and this is the variation in signal. So here, like black one is for pure cement, and this pink one is the highest percentage of fly ash. So strength is continuously decreasing as you are increasing this fly ash content. And here you have the variation for this again is 0% for this case, and this one is with the highest percentage of the fly ash. So with the increasing fly ash percentage, again here voltage is found to decrease. So here, I mean, then we can consider that whatever is the structure existing, or whatever kind of formations are existing within cements, those primarily are responsible for the occurrence of the signal, but fly ash is not contributing to it. Then here we have this compressive strength when this metal powders are added. Here just this was with the intent that okay, if we add some metal powders, then we are likely to have higher signal. That was what we expected, for the reason that metals are conducting. So if at all there are any movements of charges which are giving rise to the signals, so those movements will get some further acceleration because of the presence of a conducting material. I mean, the conducting medium is there, through that the charges can move pretty fast. But as such, this is an insulator, a cement based material, right? So with that intent we added, and yes, that happened also. Like you could see, yeah, so here it is opposite. This pink one is for the cement paste, and then you see copper in this category will have the highest conductivity, so highest voltage we obtained for the copper, followed by aluminum. Okay. So this maybe I'll skip here. Then next, most commonly used form of this cement we wanted to try. So these experiments are with the mortar. So that, because generally pure cement is not much used, either you use mortar or concrete. We could not do anything much with concrete so far, but we tried it with mortar. So these are the standard cubes of mortar. Okay, and this is the usual procedure which is prescribed for fabrication of the same. Excuse me. Yeah, now prior to this, whatever results for these non-contact signals have been shown, so those were primarily for what do you call impact, right? Impact was applied, and then we tried to obtain signals. So here we have tried it with the static loading for this particular case. So this is just a schematic showing two platens of a universal testing machine. So it's a stationary and moving platen on top, the usual configuration. Then again, these mica sheets are placed like the insulators we have been placing in the previous cases also. And then this sample is placed in between, and these lines actually are uh, sheets of copper again, just like the previous cases. We used annular kind of copper sheet, right, to work as the antenna for all the previous cases, because the samples were having a cylindrical shape. But here we had a cubic sample, so one sheet here and one sheet here, parallel, in parallel we kept them. Okay, and then the experiments are conducted. And on the same samples, actually we conducted these impact tests also, so those are depicted in this slide. So you have again the similar setup, that the weight can be held at a height and then can then be dropped onto the sample. Okay, so this is for the impact. Now one by one we can have a look at the results which are obtained for both the cases. Yeah, so this one is for the experiment done on the UTM. Okay, this is one sample signal what is obtained. But of course, so during loading, until fracture nothing was obtained, but by the time fracture occurs, then this kind of signal could be obtained. And this shows the again the variation of these signals as the number of days of curing actually increases. So beginning from close to 45 millivolt, and then it falls below close to 13 millivolt. Okay, for 28 days curated samples. And here are the results when weight is dropped on this. Okay, so here again relatively higher voltage is obtained. Like previous slide, we were varying from 10 to 40 or 13 to 40, 43 or something like that. And here it is a minimum for the 28 days cured samples. It's itself beyond 100 millivolts, so it's close to 130 millivolts. So we could say what do you call, a 10 times increase when the height of impact is only 6 centimeter. If you increase it further, then of course even higher signals are obtained. This is for 6 centimeter height. When the weight is dropped, we get this much. And yes, then again we tried to uh, have, say, some kind of formulation or a physical mechanism which might be giving rise to the occurrence of these emissions. So for that, I mean, this was a useful thing. So this is showing the variation of water content in the material. Okay, so here like you see this blue one is fraction of non-evaporable water, and this pink one is fraction of evaporable water. Okay, so this hydrated product actually has both the things. It has some amount of water which if you heat up can be evaporated. Okay, uh, this I mean at a moderate heating, you are not going to very high temperatures, then also this evaporable portion will leave the material. Okay, but this non-evaporable fraction, this actually is kind of closely knit into it. So this what do you call, that this gel formation I was mentioning, as this cement hydration progresses, so this non-evaporable part, this gel formation as takes place, so there it becomes integral with that, like all this calcium oxide or silicon of CSH gel is there, so there actually it becomes integral. But like grain growth, I think is the simplest thing to visualize. Grain growth occurs after recrystallization, if you remember, right? Then what happens at the grain boundaries? You have mismatch. So similarly here also, as this CSS gel formation takes place, then it will grow in size at different locations after nucleation, and in between you will have some space which will not be filled, where the gel formation will not take place. So there this water will tend to reside. So it is that location where you have this evaporable water content. Okay, so we tried to consider this as the primary reason for the occurrence of these signals, whatever we could observe. And then yeah, and this evaporable water, you see it is reducing similarly, like the signals also suddenly after 3 days of curing, when we attend 7 days of curing, suddenly the signal drops in the previous graph we had seen, right? So this actually shows more or less the kind of pattern what is obtained for the non-contact signals also, sudden drop and then a decreasing, further decreasing pattern. Yeah, so for the hypothesis then, what is considered is this, like I mentioned, there is a place in between gel formed zones, right? So these are these blank spaces which remain there, these are referred as capillary pores. So these capillary pores have the water which remains there, which is not used by the reaction. Okay, and this also has the ions. This has different kinds of ions, calcium, magnesium, and so on, right? Hydroxide. So I mean, some people earlier, before we tried all this, before that, some people tried some electrical properties also. So they also considered this presence of these ions for the any possible this kind of behavior, any kind of electrical conductivity, very minute, shown by this cement-based product. So here what is considered is that whatever ions are present in this water which is remaining there after the reaction, some of them tend to actually get adsorbed in the solid surface, the portion where the gel formation has already taken place. But when they get adsorbed within the surface, then another layer of the oppositely charged ions actually forms within the liquid. So this schematic is not exact, of course, but this is trying to represent that kind of thing. So say positive ions are adsorbed, this says the solid part, and in between say this is a capillary pore. So then along this line of positively charged ions and negatively charged ions will get aligned here. So this kind of a double layer formation then takes place. So the ions which are adsorbed in the layer, they will not be able to move, right? They are in the solid surface. But which are in the liquid, they can move, as liquid will be free to move whenever there is a disturbance. If no disturbance, there will be equilibrium. When there is a disturbance, then as the water moves, the charges will also move. Okay. So here what actually has been considered that, here are different possibilities, like these, once loading is done, then these ions which are in the liquid tend to move one direction, or this kind of oscillations. All these different possibilities could exist, right? This is what we in general considered. But then finally what we adopt is this. So we assume that this kind of surface here, this is representing the ions which were adsorbed in the solid phase, like here in the solid portion. Okay, and this liquid part is this middle portion, and this can be the solid phase at the opposite side. Okay, so with this then we can consider that these positive and negative segments will form the dipoles everywhere, one positive ion, one negative ion. So this kind of different sets of what do you call dipoles could be identified within this. So then with this, what do we have is that when there is equilibrium, where there is no external load, this system will be in equilibrium. One positive charge, one negative charge, they are equaling each other, no resultant anywhere, right? But then say if there is a difference, then some variation will be occurring. So this is what we have considered then for this case. Yeah, first of all, this expression is here is for the dipole moment. So if we have a electric dipole, a positive and negative charge combination, so the dipole moment is given by the charge, value of the charge multiplied by the separation distance. Okay, so this d here represents the separation distance and q is the charge. So q into d is supposed to give the dipole moment. Okay, so what we have done is we have added this another dd. Okay, so this is to represent the condition when there's some disturbance is created. Okay, so when there is no difference, this q into d is existing as such, but when there is a difference, then what will happen, this d will change. So to accommodate that, we added this another dd. Okay, so idea is like this is one layer, this is another layer, and suppose external load causes some deformation is this sample. Okay, maybe I don't know whether you are visualizing it. So this, as I had mentioned, is for one particular capillary pore, right? This thing. So these kind of will have enormous in the complete this complete cylinder. Okay, so this is something which will be at the dimensions of microns. Okay, within the range of microns, and like these simple lines are there, no? So these you can consider that there are large many uh, these micropores existing, capillary pores. Okay, so in each of them this kind of system might be existing. So that is the hypothesis. Okay, so now the thing is like this separation distance will be d, a charge associated with one dipole plus minus combination q. So q into d is giving the dipole moment. So what is considered is, suppose a load is applied on that, then strain will be produced. Say there is some compression, then what will happen? Sample gets compressed. So we just assume that as this compression takes place, then these capillary pores will also undergo compression. So of course, at the micron level, the same thing will not translate, but we went for an approximation. So we considered that whatever strain is produced for the bulk sample, we can translate the same to the capillary pore also. Okay. So with this consideration, yeah, here it is. So what we considered, say weight is dropped on the material. Okay. Some compression will occur. Thereafter, there will be some vibration before equilibrium is adopted. That is the usual thing, right? You hit anything, then it does not come to equilibrium immediately. There is some vibration. So the same thing we considered for this. So we considered the potential energy associated with the falling weight. That energy is imparted, that produces a strain. So we just converted this input energy to the strain energy of the sample. So from there we got this expression of maximum strain what could be produced. Okay. Then this we translated to these dimensions. Epsilon max for bulk one we considered, and we translated this to directly to this. Okay. Strain is dimensionless, so you just add to these dimensions and then you get in the capillary pores how much this separation distance of the dipoles will get reduced. Okay. So with that consideration, we express this variation in the separation distance in this form. So this expression, some of you might recognize, this is the usual expression for a damped vibration response, right? So we used from literature the value of damping, which is prevalent for this material. Okay, and using that we considered this kind of variation. So this we then incorporated in this expression. So this now becomes a time dependent quantity. This dipole moment here becomes time dependent. Okay, the advantage with that is, now as this is varying with time, we can differentiate and obtain its first and second time derivatives. And that again we did because we had certain relations, right, in the books of electrodynamics. Here are the relations, right? So these are the relations for the electric and magnetic field which are generated by randomly moving charges. So if you have certain charges moving around, okay, so these charges will give rise to some electric and magnetic field away from it. So this P is supposed to be away from it. Here you have all these charges which are separated here and there, they are moving. So based on them, we can get what kind of electric or magnetic field can be achieved at a further point. So these expressions we had, and these here are in terms of moving charges, and we actually have them in terms of dipole moment also. So whenever there is accelerating charge, it gives rise to radiation. Okay, likewise if you have a dipole moment variation, okay, again we'll have radiation and induction. Okay, so that is what we wanted to achieve, so that's why we obtained a dipole configuration hypothesis and its variation with time. So using that in this these expressions, yeah, and these expressions actually are in spherical coordinates, so we had to change them to cylindrical coordinates also, right? So after converting this, we got this kind of component for the electric field. So since we are using these conducting elements, right, and then obtaining the signal, so this electrical component only we are able to capture. They are supposed to produce magnetic component also, but of course that is usually very weak, and what we are able to measure is electrical component. Okay, so then further making use of this whatever is generated over here, like that this component I could say, we tried to obtain a value. So that's what then I can explain over this. And this slide particularly is telling that here what we have in this slide is electric field component because of the oscillating dipoles, right? Dipoles are oscillating like this, separation distance varying, okay, as you hit with as the deformation occurs, this kind of variation is occurring. So separation distance between two charges is undergoing variation. Okay, so because of that, what we are getting is given here. Now next, then what we are getting at oscilloscope is that is the voltage according to our measurement technique. This is something which is generated by the material. Okay, but then next is what we are observing. So for that, then we use this kind of formulation to convert it to voltage. Okay, so for cylindrical component, of course, web parameters we have to consider, and from the generated charge we finally get the voltage expression. Yeah, so here is a comparison. So this is representing whatever we experimentally observe, right? Whatever signals we could obtain experimentally, those are placed all over here, and these are the ones which have been calculated. Okay, so of course according to the assumed damping of the material available in literature, damping is a bit after a longer duration, but the amplitude we could match to a great extent, as you can see here. So this one is the experimental result, this is the theoretical, this whatever theoretical model we could propose, with that we got this one. So it's fairly close because this is most basic model, I would say, completely new hypothesis we could come up with, right? So fairly close thing we could obtain. And yeah, then the same thing we further extended for the mortar sample. There the geometry was entirely different, right? It cubical, and then the antenna types what we are trying to use were rectangular sheets at the two sides, right? So then now again we had to convert everything to rectangular components, and with the geometric parameters associated with the this particular experiment. And here also then finally we could get matching results. So this one again is representing this, what do you call, comparison of experimental and theoretical results, and this is comparison of their amplitudes for both the cases. Again, a similar job. and this again the variation of evaporable water content and non-evaporable. So this maybe I'll just skip. Yeah. Then here this just a 3D plot. Here again applied mechanical energy, so corresponding to each dropping weight, whatever is the variation of height, how much energy is applied, that is actually taken into account, and the EMR voltage has been plotted, and again the number of days of curing, 3, 7, 14, 28. So an increasing pattern, of course, for 3 days highest value, and then it reaches very minimal value afterwards. And also the variation of dominant frequency here you can see. So for this we actually did the fast Fourier transformation images, we obtained from the signals, and then we obtained the dominant frequency. So that could also be a important parameter for the measurement, because depending on different frequency range you need to end up having different kinds of antenna if you want to increase the distance and so on, right? So this shows that variation. And yeah, so this is just to establish that this theory whatever we had developed, that was with the oscillating dipoles. So that again, I mean, there we did not consider any incipient damage to the material. So usually prior to this theory, whatever were given, those were based on a permanent damage. I mean, those phenomenon and other things like during plastic deformation or propagation of crack and so on. So here we just wanted to establish that it is, I mean, without damage also we are getting a signal. So early warning it could actually give us. So here this one just confirms to that once the fracture occurs, the overall signal strength actually is pretty less, but before that relatively higher magnitudes are obtained in this. And yeah, so then maybe I could just conclude within few minutes with this one more additional thing. So we considered two things. One was, of course, to begin with piezoelectric materials, because they tend to give pretty high signals in general and have been used for sensing applications a lot, right? And then we considered the structural materials. So cement is what we actually next moved on to. So next here is an attempt to get higher voltage signals with a combination of both. So we have seen that when we used pure cement, then suddenly the order of magnitude reduced pretty low by 1000, right? 10 to the power 3. So now this actually is with the uh, composite of cement as well as PZT, so that we could get some higher values. Yeah, so here we have some results with for the pure cement and PZT samples, a variation of PZT content from 5%, 10% up to 40%. So here we have, this one is the lowest one is for the 5%. Here we don't have for the pure cement, but I remember it was pretty low, some value. Whatever we had. So a sudden jump, of course, you have in it, and as this amount of PZT is increased, then of course higher value we have. Maybe we go to the next slide. This is for the mortar samples, again with a variation from 0% up to 40%. These are the sample plots, and if you compare, yeah, so here you have it for the 0% PZT, that is pure mortar sample. So here you have here if you compare the sample, it is close to again 125 or something, okay. But if we add 5% PZT, so this one is quite noticeable change you can say. As you add 5% PZT, from here we reach up to this point, so a sudden increase is obtained. So of course then using then what do you call PZT or any other piezoelectric material in any case can enhance the signal obtained to a great extent. So this we can say close to 2.5 times even at the height of 6.5 centimeter, as you can see. Again, the variation of the dominant frequency here linearly increasing again as the height of impact is increased and higher frequency range you are achieving. And then this another interesting result, I would say that as we are mixing PZT in this mortar samples, so this actually is giving better strength. So somehow it is assisting with the mixing probably, or a better distribution of the hydrated project. So this I mean in a way is what do you call, a promising result, in the sense that say when we try to incorporate some kind of sensor with the structure like earlier I mentioned, then it's likely to affect the properties of the base material or base structure itself. Okay. Now, if we say mix this PZT to this mortar mixture and then it is giving better strength, then at least it is affecting in positive sense. It is not adversely affecting. So, if we wish to later on consider this kind of small blocks for obtaining the signals, the structure will not get adversely affected. So, we can incorporate it without any damage or without any bad effect on the base structure. Okay, so with this then maybe I'll end this, and if you have any questions we can have them. Yeah, tell. Mm, should I go to the first slide? PZT thing you are saying? This one. Okay, sample sizes are different. So if you consider this one, I think this had an height of about 8 mm and a width about 12 mm, a diameter of 12 mm. This one, and then the PZT one, yeah, here. So these had a higher height. These had a 15 mm height but 6 mm diameter. These we had bought. These we did not make. PZT we had bought ready made. Yeah, the sample sizes remained the same. The PZT always 6 mm diameter and 15 mm height, right? For both, only the setup changed, setup to apply impact, but the size of sample remained same. No, exactly. Okay. Yeah, I mean not for PZT, but for BT we have done it, but I don't have on this slide, so maybe I can tell you separately. So I mean this thing, these thing what we have done this with the electrical field input. For this we have a framework theoretical model. So there we considered like piezoelectricity. If you have studied in your material science somewhere, I don't know whether you have done or not. So usually you have this structure of BT is most popular to show. So what happens is in the ferroelectric materials, this ferroelectricity arises because of the dipole formation within the unit cell. So unit cell is not say uniform, there is some deviation. So it's referred as non-centrosymmetric structure, because at the center what is the symmetrical position, that is lost, some variation occurs. Oxygen and barium, they actually shift, or like titanium and oxygen atoms are shifted. So what happens is a positive and negative uh, dipole formation takes place. So barium or titanium ions, these remain positive, so oxygen will be negative. So some separation from their symmetric position. So that leads to this dipole formation. So based on that, then we had considered oscillations of dipoles like alternatingly. So we considered the usual model of electrical dipole. Again, usually you find in textbooks for electrodynamics, one positive ion, one negative ion, and if they oscillate from one to right. So based on that, that model we have made, but at the moment on the slides I don't have. Oh, no, no, all are different. So I have to give, say, I have to acknowledge more than one PhD scholar for this, not one person's work. Yeah. No, no, no. Electromagnetic is for radiations. Radiations are electromagnetic radiations which are occurring. For that probably. So that we used as abbreviation EMR. Yeah. So that is the thing which we are trying to obtain non-contact sensing using which. So we are trying to get this electromagnetic radiation signals for the purpose of sensing. So that is it. Okay. Yeah. So if anyone else has got any questions? Hmm? None. Okay. So thank you so much for participating and